Swayam Prabha. Digital India. Educated India.
So, in the last class we discussed three different control schemes: proportional controller, proportional integral controller and proportional integral derivative controllers. We discussed P only controller having the transfer function of Gc equals Kc. We discussed Pi controller having the transfer function of Gc equals Kc 1 plus 1 divided by tau is. We discussed the PID controller having the transfer function of Gc equals Kc 1 plus 1 divided by tau is plus tau ds. Fine. Now, here Kc is basically the proportional gain, Kc is the proportional gain, and this gain equals del output, I mean change in output per unit change in input. So, the unit of Kc depends on the unit of output as well as input. The unit of proportional gain Kc depends on the unit of output as well as the unit of input, and tau I is the integral time constant. Tau I is the integral time constant. The unit of tau I is time, I mean it may be minute, may be hour. So, the unit of integral time constant is say minute. Another term which is involved in derivative term, that is tau d. Tau d is derivative time constant. Tau d is derivative time constant. Unit of derivative time constant is minute or it may be hour. Fine. So, these three parameters are basically the control parameters. Kc, tau I and tau d are the control parameters. Kc, tau I and tau d are the control parameters. Tuning of these parameters will be discussed later. How we can select the values of these three tuning parameters, that will be discussed later. Fine. So, today we will start with the dynamic behavior of closed loop process. Today we will discuss the dynamic behavior of a closed loop process. First we will discuss in generalized form, then we will consider few specific cases, we will consider few examples. Now, to discuss this we need to develop the block diagram of the closed loop process. Fine, the block diagram of closed loop process we already discussed in the previous class. So, I am just redrawing the block diagram of a typical closed loop process. So, this block is representing the process having the transfer function of g suffix p. This block is representing the process having the transfer function of g suffix p. M is the input to the process. M is the input to the process, which is basically the output of final control element. Now, the output of this is added with this output. Fine. These two outputs are added. D is the disturbance and GD is the transfer function of the process with respect to disturbance. Output is y bar. Process output is represented by y and in Laplace domain that is y bar. Now, what is done? First the process output is measured using a measuring device. The process output is measured using a measuring device. Say the measuring device has the transfer function of Gm. We are representing the transfer function of the measuring device by Gm. Now, the measured output usually differs from the actual output. So, we will represent the measured output by Ym. The measured output we are representing by y suffix m. Then this measured output is compared with the set point value of process output. The measured output is compared in the comparator with its set point value. The output of this comparator is epsilon and this output is supplied to the controller. This output is supplied to the controller. The controller transfer function we are representing by Gc. Controller output is say C. We are representing the controller output by C and this C is implemented through the final control element FCE. Controller output C is implemented through final control element C E, and this final control element has the transfer function of suppose Z suffix f. The transfer function of the final control element is suppose Z suffix f. So, this is the block diagram of a closed loop system. Block diagram of a closed loop system. Now, we will discuss different elements of this closed loop transfer function. Different elements are process, measuring device, controller, final control element. These are the different elements of this closed loop process. One is the process, another one is measuring device, then controller and final control element. And we will try to represent these elements by mathematical forms. So, if we consider the process, we can write for the process y bar equals y bar s equals G P s multiplied by m bar s plus Z D s d bar s. Can we write this? The process can be, for the process we can write this equation. These two signals are added, this and this signal is added. Now, this equation is representing the process. Next one is the measuring device. Measuring device. Measuring device output is ym. So, in Laplace domain ym bar s equals Gms y bar s. For the measuring device we can write this equation, output equals transfer function multiplied by input. Next element is the controller. The input signal to the controller epsilon bar equals y set point bar s minus y m bar s. Input signal to the controller epsilon equals y set point minus y m. This is representing the comparator. Similarly, the controller output is C bar s, controller transfer function is GCS and input to the controller is epsilon. So, C bar s equals GCS multiplied by epsilon bar s. This is representing the control block. Now, final control element FCE. For final control element, the output is m bar, transfer function is ZF and input is C bar s. So, for final control element we can write output m equals transfer function GC multiplied by C. Fine. Now, this m bar s we can write again as GF multiplied by CS. CS means what? CS means GCS multiplied by epsilon bar S. Can we write this? CS equals GCS multiplied by epsilon bar S. Now, we will substitute the expression for epsilon bar S now. So, GF GC epsilon bar S is y set point bar minus ym bar, fine. Epsilon bar S is y set point bar S minus ym bar S. In the next step, we will substitute the expression of ym. So, GF GC y set point bar minus ym bar. What is the expression of ym bar? GMS multiplied by y bar S. Fine. We are not writing S anymore. So, this is the expression of m bar. Agree? Now, we have written the expression for the process as y bar equals Gp m bar plus Gd d bar. We have written this equation previously for the process. Fine. Now, here we will substitute the expression of m bar. Here we will substitute the expression of m bar. So, Gp multiplied by m bar, that means GF GC y set point minus GM y bar. This is m bar. Now, the second term is Gd d bar. Fine. We have just substituted the expression of m bar in the equation of process. Now, if we rearrange this equation, we finally get y bar equals Gp Gf Gc divided by 1 plus Gp Gf Gc Gm y set point bar plus second term is Gd divided by 1 plus Gp Gf Gc Gm d bar. By rearranging, we get this equation. Now, the first right hand term, this provides the effect of y set point on y. The first term provides the effect of y set point on y. So, it provides the effect of y set point on y. Similarly, the second term, second right hand term provides the effect of disturbance on y. The second term of this equation provides the effect of disturbance on y. Now, this equation is the closed loop transfer function. This equation is called closed loop transfer function, CLTF. Fine. This is the expression of closed loop transfer function. Now, if we consider GF, GC equals Z, considering GP, GF, GC equals Z, we get the closed loop transfer function as y bar equals Z divided by 1 plus ZGM y set point bar plus ZD divided by 1 plus G multiplied by GM D bar. Fine. Considering GP, GF, GC equals Z, we get this form of closed loop transfer function. Now, again we will consider this as Z set point multiplied by YSP plus Z load multiplied by D bar, where G set point equals G divided by 1 plus GGM and Z load equals ZD divided by 1 plus ZGM. Considering these two expressions for G set point and G load, finally we get this closed loop transfer function. Can we develop the corresponding block diagram? What will be the block diagram of this final form of closed loop transfer function? It is very simple. We can consider one block for Z set point. What is the input? Input is Y set point. Now, this output is added with the output of this load block. I mean, these two outputs are added and finally we get Y. Fine. This is the block diagram of the final closed loop transfer function. So, our original transfer function is GC, GP, GF divided by 1 plus GC, GP, GF, GM Y set point bar plus ZD divided by 1 plus GC, GP, GF, GM D bar. We will use this transfer function mostly in the analysis of different features. Fine. You see here the transfer function of measuring device does not exist in the numerator, and in the denominator, in this term particularly, all the transfer functions are included. All the individual transfer functions are included in the denominator. Fine. Now, the control performance is usually investigated by performing two tests. One is servo test, another one is regulatory test. The control performance is usually investigated by performing two tests. One is the servo test, another one is the regulatory test. So, what is servo test? In the case of servo test, there is no change introduced in the disturbance. In the servo test, there is no change introduced in the disturbance. That means d bar equals 0. Only the set point change is considered. Fine. Now, if d bar becomes 0, what is the closed loop transfer function for the servo problem? So, closed loop transfer function for the servo problem becomes GC GP GF divided by 1 plus GC GP GF GM y set point. This is the closed loop transfer function for the servo problem. Now, introducing step change, maybe sinusoidal change in y set point, and by taking inverse of Laplace transform, we can know the transient response yt. Fine. By that way, we can test the controller. Now, this is called servo problem, and sometimes another term is used, that is set point tracking. So, set point tracking performance is observed by performing servo test. Another test is regulatory test. Regulatory test is conducted by considering no change in set point. That means y set point bar equals 0. Regulatory test is conducted by considering no change in the set point value. Accordingly, the closed loop transfer function becomes y bar equals ZD divided by 1 plus GC GP GF GM d bar. So, this is the closed loop transfer function for the case of regulatory problem. Another term is again used for this, that is disturbance rejection performance. So, to observe the disturbance rejection performance of a controller, regulatory test is conducted. Set point tracking performance is observed by conducting servo test, and disturbance rejection performance is observed by conducting regulatory test. So, next we will consider one example to discuss the formation of closed loop block diagram. So, formation of closed loop block diagram. For a liquid level system. Liquid level system. We will discuss the formation of block diagram for a liquid level system. So, first we will draw the schematic of liquid level system. This is the liquid tank, Fi is the inlet flow rate and outlet flow rate is say F naught. Height of liquid in the tank is H. Fine. Now, the objective is to maintain the liquid height in the tank by manipulating the outlet flow rate. The objective is to maintain the liquid height in the tank at its desired value. Accordingly, height is the controlled variable. So, there are two options of manipulated variable. I mean, we can select either Fi or F naught. Suppose F naught is the manipulated variable, then what will be the load variable? Fi. If we consider F naught as the manipulated variable, then Fi will be the load variable. Now, we will consider the different elements. So, first we will consider the process. First we will consider the process. I mean, we need to develop the transfer function of the process in terms of GP and GD. So, for developing the transfer function of a process, we need the model. So, model we can represent by this ordinary differential equation, A dH dt equals Fi minus F naught. This is a modeling equation for the liquid level system. Now, here we are not using prime to represent the deviation variable. We are not representing the prime superscript to indicate the deviation variable. I mean, H, Fi, F naught, these are deviation variables. Fine. So, this equation is written in terms of deviation variables. We are not representing prime superscripts. If we take Laplace transform, then we get AS H bar S equals FIS minus F naught S. Taking Laplace transform, we get this form. Now, rearranging H bar S becomes 1 by AS multiplied by F bar S minus 1 by AS F naught bar S. Fine. Dividing both sides by AS, we get this equation. Now, what is the general form? See, general form is Y bar S equals ZPS M bar S plus ZDS D bar S. This is the general form, and this is for the liquid tank system. Comparing these last two equations, we can easily get the transfer function GP and GD. So, what is GP? Sure, GP is 1 by S. Yes, GP is minus 1 by AS, because our disturbance is Fi and M is F naught. Here M is F naught and disturbance D is Fi. So, we get the transfer function GPS equals minus 1 by AS, and we get ZDS equals 1 by AS. Fine. So, these two transfer functions we obtain. Now, what about the next element? I mean, what is the next element? Next element is the measuring device. So, we will consider the measuring device for finding the transfer function. Here, I mean, in this liquid level system, first we can configure the control scheme. If we configure the control scheme, then we need the final control element. Sorry, first we need the measuring device. So, to measure this liquid height, the differential pressure cell is extensively used. To measure the liquid height, differential pressure cell DPC can be used as a sensor. So, what is the output of this differential pressure cell? HM. The output of this differential pressure cell is HM. Original height is H and measured height is HM. This output is compared with the set point value HSP. Measured height is compared with set point value. Then this error signal is supplied to the controller and controller action is implemented through the final control element. This is the control configuration of the example liquid level system. So, here measuring device is the differential pressure cell. We need to find the transfer function of that differential pressure cell. What is the input to this differential pressure cell? Input is the pressure difference del P. Input to the differential pressure cell is the pressure difference del P, and we can consider del P proportional to liquid height. This del P is proportional to liquid height. What is the output of this differential pressure cell? H suffix M. So, input to the differential pressure cell is differential pressure, pressure difference, and output is HM. Fine. Now, considering second order dynamics of this differential pressure cell, we can write the modeling equation as tau square d2 Hm by dt square plus 2 zeta tau dHm dt plus Hm equals Kp del P. Fine. Considering second order dynamics of the differential pressure cell, we can write this equation. Now, the right hand side is Kp del P. So, we can write again, that is equal to Kp beta H. Del P is proportional to height. So, del P equals beta height, beta multiplied by H. Fine. Taking Laplace transform and rearranging, we get the transfer function as ZMS equals output Hm bar S divided by input H bar S, which is equal to Kp beta divided by tau square S square plus 2 zeta tau S plus 1. Taking Laplace transform and rearranging, we get finally this transfer function for the measuring device. Fine. Next element is the controller. Next element is the controller. We know the transfer function for P, PI, PID controllers. Now, if we consider the PI controller, then the transfer function we can write as GC equals KC 1 plus 1 divided by tau by S. If we consider PI controller for the example liquid level system, then we can write the transfer function in this form. Fine. Another element is the final control element. Another element is the final control element. Assuming first order dynamics of the control valve, we can write the transfer function as Gc equals Kv divided by tau Vs plus 1. Assuming first order dynamics of the control valve, we can write the transfer function as Gv, this is Gf, this is Gf. So, Gf equals Kv divided by tau Vs plus 1. Kv is the gain of the control valve, Kv is the gain of the control valve, and tau V is the time constant, tau V is the time constant. Can you make the closed loop block diagram now? We can now make the closed loop block diagram. First, we need to develop the process having the transfer function of Gp and Gd. How much is Gp? Gp is minus 1 by s, Gp is minus 1 by as. What is Gd? Gd is 1 by as, fine. And what is the disturbance? Disturbance is Fi. What is the output? Output is height. And what is the input to the process? I mean, what is the final control element output? That is F naught. So, this is the process. The transfer function of the process with respect to F naught is minus 1 by as. Transfer function of the process with respect to Fi is 1 by as. Output of that process is H. Measuring device, for the measuring device we have derived the transfer function, that is Kp beta. Kp is the gain of the measuring device whole divided by tau square s square plus 2 zeta tau s plus 1. So, this is the transfer function of measuring device. I mean, this is equal to Gm. Output is measured height, this is the comparator, H set point is compared with this measured height, then the error signal goes to the controller, which has the transfer function of Kc 1 plus 1 divided by tau is. This is the transfer function of the controller, PI controller. Output is C bar. The transfer function for the final control element we have derived, that is Kf equals Kv divided by tau Vs plus 1. This is the transfer function of the final control element, fine. So, this is the block diagram of the example liquid level system. This is the closed loop block diagram of the liquid level system. Fine. Okay, in the next we will discuss the effect of proportional action. We discussed the three controllers P, Pi and PID. Basically there are three actions. One is proportional action, another one is integral action and derivative action. So we wish to discuss the effect of all these actions individually. So first we will discuss the effect of proportional action. So first we will discuss the effect of proportional control. We can write proportional action or proportional control because it only includes the proportional action. For this purpose we will consider one process, one open loop process we need to consider. So first we will consider an open loop process. Fine. First we will consider one open loop process. Now to observe the effect of proportional controller we need to close the loop. So for closing what we need? We need one controller, that is P only controller because we are going to discuss the effect of P only controller. Then we need one measuring device, and also we need one final control element to implement the control action. So for observing the effect of proportional controller we need to consider a process, that is open loop process. Now to close the loop we need to include the controller, we need to include the measuring device and final control element. So what open loop process we will consider? We will consider two processes, one is first order process and second one is second order process, and we will discuss one by one. So first we will consider first order process. In the next we will consider second order process example. In the next we will consider second order process. Next element is the controller. So here we will include the P only controller. So for P only controller what will be the transfer function? For P only controller the transfer function GC equals KC. So for P only controller the transfer function is GC equals KC. For measuring device we will consider GM equals 1, and for final control element we will consider GF equals 1. So for simplicity we are assuming the transfer function of measuring device and final control element both are 1. Fine. So we will start from the closed loop transfer function. We will start from the closed loop transfer function. The general form of closed loop transfer function is y bar equals GC GP GF divided by 1 plus GC GP GF GM y set point bar plus ZD divided by 1 plus Gc, Gp, Gf, Gm d bar. This is the general form of closed loop transfer function. Now, in this closed loop transfer function, we need to substitute the individual transfer functions. Like for the process, it is mentioned that first we will consider first order process, that means Gp equals Kp divided by tau Ps plus 1. For a first order process, this is the transfer function. Now, if we substitute the transfer function Gp, Gc equals Kc, Gf, Gm equal to 1, then what we will get? If we substitute all the transfer functions, then we will get the closed loop transfer function for this example system. Now, for the process, this is the transfer function with respect to manipulated variable. Another transfer function is involved, that is Gd with respect to disturbance. So, what that will be? So, for that purpose, we will first consider the process. We need to write the modeling equation for the process. The modeling equation for the process we can write as tau p dy dt plus y equals kpm plus kdd. The first order process we can represent in time domain by this form, where y is the output, m is the input to the process, m is basically the output of the final control element, and d is the disturbance. D is the disturbance, and y, m and d all are in terms of deviation variables, all are deviation variables. Now, Kp is the gain of the process with respect to m. Kp is the gain of the process with respect to m. Another gain is involved in this equation, that is Kd. Kd is the gain with respect to disturbance. Fine. Now, if we take Laplace transform and if we rearrange, then finally we get y bar s equals Kp divided by tau Ps plus 1 m bar s plus Kd divided by tau Ps plus 1 d bar s. Taking Laplace transform and rearranging, we get y bar s equals Kp divided by tau Ps m bar s plus Kd divided by tau Ps d bar s. So, Gp is equal to Kp divided by tau Ps plus 1 and Gd is equal to Kd divided by tau Ps plus 1. Fine. From this equation we can get the transfer function of the process with respect to m, that is Gp, and the transfer function of the process with respect to disturbance, that is Gd. Now, all individual transfer functions are known to us, Gp, Gd, Gc, Gf and Gm. So, in the next step we need to substitute all these transfer functions in the closed loop transfer function. So, that we will discuss in the next class. Thank you.